singularities in them? Just like
not good ones. Usually that's a sign of a breakdown in the theory. You know?
Newtonian gravity or like classical electrodynamics have like infinite energies on charge.
Yeah, so we have to fix that, right? We don't think that's the complete. We don't think that's the complete story. Now, in Newtonian gravity, you know something happens when you get to very high densities. Okay, you now have to use. Gravity becomes strong. You now move to general relativity, but general relativity, while it addresses some issues, doesn't get rid of the singularity aspect of the problem. It remains with us. So here it is. But we don't think we should just settle with that.
But is that like a cosmology problem or like a general relativity problem?
It's both. Yeah. It's a general relativity problem. That general relativity has singularities. It also has singularities in the centers of black holes, for example. And it's a kind of incompleteness problem. That the theory is because things are blowing up and you don't have any. It's a sign that the theory is incomplete. We need to know what happens when physically we really get to that.
So you don't think there are really singularities in black holes?
Yeah, I think we think that's an assumption. That is an extrapolation of Einstein gravity to the center of a black hole. So when things blow up in your theory, then you should be concerned that your theory is incomplete. That's a sign that it's being incomplete. Usually it means there's some kind of process at some microscopic scale. If like you might have shock theories where shocks are looked to be singular, but then if you understand that really your substance is made of atoms and molecules, or somehow on the atomic scale there's a cutoff and a correction to your theory, an enhancement of your theory that tells you what to do there. In this case, the enhancement you expect is that well before you reach the singularity, either in a black hole or cosmologically, I shouldn't say well before, but before you reach the singularity, you already reach a point where quantum effects, quantum fluctuations in space and time, invalidate the equations you're using, because you can't even sensibly describe classically a metric once you get to those temperatures and densities. So you shouldn't simply plow through and ignore that and use the same equations and expect that they're going to describe things correctly. So that's part of the that's one of the reasons why we're interested in quantum gravity, because it's going to help us fill in the story. And one of the challenges for quantum gravity is, big challenges are these singularity problems in black holes and cosmologically. So, if you know that the leading ideas we have today for quantum gravity involve string theory in some way, but at this point string theory is not well developed enough to answer either of these two questions. What replaces the singularity? And how do we go from a quantum-dominated phase to a classical-dominated phase? So those remain open issues. So they remain open issues for cosmology. Okay, so a dominant idea at present in cosmology, which relates to these issues, is the idea of inflation. So let's discuss that a little bit. Dominant, simply many cosmologists pursue this idea. Doesn't mean it's the right idea, doesn't mean it's the winning idea, it's just an idea that you read a lot about. Now, it's important to realize inflation involves events after the singularity and after the quantum to classical transition. It assumes that those things already occur. So this definitely has no impact. It skips the singularity problem. And it skips the quantum to classical transition issue. So Big Bang inflationary cosmology is, at best, incomplete in the same sense that in this sense, is that Big Bang is complete. It's meant to focus on these other problems. So it's assuming that you're already, you can describe things well by quantum gravity or some similar classical theory of general relativity. And its idea, and its goal is to introduce a mechanism, inflation, that's going to address these other issues, to explain the smoothness of the universe, the flatness of the universe. And focuses the other problems And the idea is to introduce some extended period, extended but finite period of accelerated expansion. Let's walk through that phrase a bit. By extended, I mean it has to last long enough to accomplish its goal of solving these problems. It's not just a matter of getting accelerated expansion for a brief instant. It has to last long enough in order to do the job. Okay. In this case, that's going to mean that you need it to last long enough that compared to the Hubble time when it starts, it has to last at least 60 Hubble times. Where does that 60 come from? Well, it's related to this 10 to the 30th problem that we have over here, which is e to the 60, roughly, so I'm using in the approximation. I'm using, that's where it's coming from. I need to solve a problem which is 10 to the 30th or e to the 60th in magnitude, and I'm going to need expansion to last for that many e-fold, that many doublings, expansion times of the universe, or doubling times or Hubble times of the universe. So that's what the extended means. On the other hand, I better not have it last forever. It's got to have an end, because I want to then have it end and convert, and the universe then become dominated by matter and radiation. So, whatever means I'm going to use to cause the inflation, I want to be able to find some way. It has to have both a beginning and an end. I have to be able to get it to end early enough that we can recover all the successful predictions of the Big Bang model, which rely on there being matter, radiation, dark energy, and all that stuff. So it's got to have a finite period. That's where the finite period comes in. And the accelerated expansion comes in because accelerated expansion means that A double dot is greater than 0. And if you look at our Friedmann equation, our second Friedmann equation, you see that in order for that to occur, that means that the quantity we're calling epsilon has to be less than 1. And if we're less than 1, then we are escaping from, we're beginning to escape. That's as Rita was bringing up. Now when epsilon is less than 1, then all these exponents change signs. So that means that that's going to be the way we're going to escape from these problems, is to have an extended period in which epsilon is greater than 1, epsilon is less than 1 rather than greater than 1. That reverses the way all the trends, reverses the way the path size is compared to the horizon size. So that when we go back in time, although as long as we're matter and radiation dominated and decelerating, as we go back in time, the horizon size is getting smaller than the path size. If I now hit a period where epsilon is now less than 1, the two reversed. Now the horizon size begins to shrink less fast than the patch size. And if you extend it long enough, eventually you can get a patch to fit within a single horizon. So that's the amount of extent to which we want to continue the process. So that if we were to blow up this picture over here into the very corner, now we're blowing it up. For reasons not yet explained, we're imagining the inflation occurs around 10 to the 15th GeV. If we were to blow things up so that we're now looking at just a tiny little corner of that wedge, okay, where up to that point, let's see if I can draw this, whereas up to that point, the horizon size was, in this blow-up, whereas up to this point, the horizon size was shrinking faster than the patch size. So this is where epsilon is greater than 1. If we go back and hit a point where epsilon is now less than 1, now the patch size remains nearly constant. Sorry, the horizon size remains nearly constant while the patch size continues to shrink, and we eventually reach a point here where now the horizon size on this side is now bigger than the patch size. Instead